Okay, great. So, how do we show that if it's closed and bounded, it must be compact? Well, check this out. This is so cool, this proof. Look, K is bounded implies, if K is bounded, what does that mean? Well, that means K lives in some what? In some ball, and we're just going to do intervals, but if you want to do Rn, you could do K cells or whatever, right? Would you agree that K lives in some interval? An interval sufficiently big enough, right? Maybe from minus R to R for some R, would you agree? And if it lives in open minus R to R, wouldn't you agree it also lives in closed minus R to R? That's what it means to be bounded. Would you agree this is a consequence of being bounded? Yes? Oh, great. But what is minus R to R? It's an interval. It's a closed interval that therefore is what? Compact. Excellent. So you have a compact set, and K is a closed subset of a compact set, and therefore K is compact. Nice. Lots of, that was very easy. But K is compact, and this minus R to R, sorry, K is closed because it's, that was the assumption. Minus R to R is compact by the previous theorem. So K is compact also by a theorem. End of story. So showing this for closed intervals being compact was essential. I mean, was basically we did a lot of hard work there, and now we're just reaping the benefits. Okay. So any subset of R that's closed and bounded is compact. Now, what would change if I were doing this in Rn? We just have to show that a K cell is in fact compact, which the same argument would also work, right? Instead of intervals, we'd have boxes that you would do what? Subdivide the boxes into tinier boxes, yes? Okay. And you want to prove a nested interval theorem, nested box theorem for RK, which would follow pretty much the same proof as up here for nested intervals. Okay? Emil. The product of you could show the product of compact sets is compact. There's some work involved there as well, right? Yeah, I wouldn't say that it's I wouldn't say that it's an easier approach, but it's certainly true. The product of a pair of compact sets is compact. It's not true for, well, product of pair of compact sets is compact. Okay, and I can't even say what it means to be true for arbitrary products until we define what the open sets are for the arbitrary product. Okay, and for a particular choice, it'll be true for arbitrary products as well, and that's known as Tikhonov's theorem. Yes? Ooh, you guys are asking great questions. Okay, before I answer that, let me just write this down here because I want to make sure it's in your notes as well. So for RK, replace the interval by a K cell. Okay, so your question was, where does this break down if R has some other metric or some other notion of distance? Excellent question. So is it the case that AB is compact with another metric? Certainly this argument rests on the fact that this interval is compact, right? So now let's look at this interval. Suppose I give it the discrete metric. Discrete metric says distance is 0 if they're the same point, and 1 if they're not. Is that compact? for an infinite set, in fact, an uncountably infinite set? No, it's not compact. Why is that? Because you could cover every point with a ball of radius 1/2. That's an open cover, where every point is precisely one element of the cover. So you can't remove any of them and still be a cover. So that, under the discrete metric, is not compact. So then maybe you're asking, where does this proof break down? Well, if this were the discrete metric, then you're resting on the nested interval theorem, right? Right? Where does this break down? Certainly, at least one of the halves has no finite subcover. Yes, this is where it breaks down. So x is a point, right? And what does it mean to be in some set of the cover, whatever it is? Well, it's interior, but the interior of such a point is not actually an interval for a discrete metric. That's right. So this point would be, it's an interior point, but the only thing in that interior set is just a single point. And so you'd never be able to have the contradiction that the cover necessarily covers one of these blue things, which is where the contradiction came. Excellent question. Love those questions. Keep them coming, even though it forces me to think on the spot as well. Okay, any other questions about the Heine-Borel theorem? Now that we've discussed this, can you think of an example where the reverse implication is not true? Give me a metric space where the reverse implication is not true. Closed and bounded, but not compact. Discrete metric on a infinite set. Yeah, discrete metric on an infinite set. So example, let's take a discrete metric on an infinite set. The entire space is compact. The entire space, let's call this infinite set A. Well, then A is compact, is closed. Why is it closed? It contains all its limit points, which namely are, if it's discrete, does it have any limit points? No, because everything can be separated by these isolated balls. So it's definitely closed. Is it bounded? If all distances between points that are different are 1. Is it bounded? Yes, everything's in a ball of radius 2 around any of the points. Good. But is it compact? No, because you can't remove any element of the cover if the cover is balls of size 1/2. Okay. On your homework, you're going to explore other examples. Another example. Let me give you a related example, because I want to begin to have you thinking about metric spaces that are not just R or Rn. So here's another example. We don't yet even know what these words mean, but assume, based on your calculus understanding that you do, you know what the word continuous means. But that's coming up in several lectures. Remember, you could put a metric on a function space. Let's say C of R is the set of all continuous functions, f from R to R, where this R represents the domain. Okay. Continuous functions on R is the way we read it. And let's make the metric between any 2 points just the suprema metric, which is the distance between f and g for all x in R. Oh, and I probably should make sure that this distance is always defined. It might not be if this soup gets too big. So let's just make sure, let's just say that these are all, let's say these are bounded functions. So the little b refers to bounded functions on R. Okay, so the distance between any two